In this video, we're going to take a look at some of the relationships that exist in special right triangles. This falls under the learning target. I can prove theorems about similar triangles and their properties. There are two different types of special right triangles that we're going to deal with. An isosceles right triangle, also known as a 45-45-90 triangle that appears on the left, and also a 30-60-90 triangle that appears on the right. In a 45-45-90 triangle, you'll notice, since it's isosceles, we have two congruent sides. Those are known as x. And the hypotenuse, the one across from 90 degrees, is always whatever x is times the square root of 2. So x times the square root of 2, which here is written as the square root of 2 times x. In a 30-60-90 triangle, the side that's across from 30 degrees is labeled as x. The side that's across from 90 degrees is twice that, and the side that is across from 60 degrees is this x times the square root of 3, or square root of 3 times x. In this first sample problem, I notice that I'm dealing with a 45-45-90 triangle, or an isosceles right triangle. If I mark out the pattern, I know that both of my legs are x, and my hypotenuse is whatever x is times the square root of 2. So in this case, I know that these two side lengths are equal. So transferring this information over to my diagram, I have x, x, and x times the square root of 2. Well, we can see that x, we already know, is 2. And since a is the same thing, I know a is also equal to 2. And to plug in for c, I'm going to take this 2 for my x and plug it in for x into that expression, and I'm left with 2 times the square root of 2. Here's another example of a 45-45-90 triangle, or an isosceles right triangle. I'm going to start by sketching out my pattern again. All isosceles triangles follow this pattern: x, x, x times the square root of 2. I'm going to translate this pattern over to my diagram: x, x, x times the square root of 2. You'll notice that in this case my hypotenuse is labeled, so I know that x times the square root of 2 is equal to 10. It's my job to figure out what x is. Alright, so to get x all by itself, I'm going to divide both sides by the square root of 2. These reduce, and I'm left with x equals 10 over the square root of 2. Now, it's considered bad math etiquette to keep a square root sign on the bottom, so we're going to get rid of it. So we know that we can multiply this expression by 1 and not change it, but that doesn't really help us out much. But I know that the square root of 2 divided by the square root of 2 is also 1. So here I'm essentially multiplying by 1, but it just looks a little different. So I'm going to multiply here. So up top I squish 10 times the square root of 2. And on the bottom, the square root of 2 times the square root of 2 is the square root of 4, which just turns out to be 2 again. Now I can reduce. 10 divided by 2 turns out to be 5 times the square root of 2. So I've just figured out x. So these two missing side lengths are 5 times the square root of 2 each. Now we'll take a look at a 30-60-90 triangle. And before I look at my diagram, I'm going to sketch it out to get my pattern. Across from 30 is x. Across from 90 is 2x, and across from 60 is x times the square root of 3. So I'm going to copy that down onto my problem. Across from 30 is x, across from 90 is 2x, and across from 60 is x times the square root of 3. Well, I notice right away that x is 7. So now all I'm left to do is to plug in. So to figure out y, my longest side here, I'm going to plug in 2 times 7, which gives me 14. To figure out the length of x, I'll plug in 7 for x, so I have 7 times the square root of 3. And here are my missing side lengths. In this last problem, we'll take a look at a 30-60-90 triangle again. I'll begin by sketching out my pattern for my 30-60-90 triangle. Across from 30 degrees is always x, across from 90 is 2x, and across from 60 is x times the square root of 3. And I'll copy that down. So across from 60 is x, it's already labeled that way. Across from 90 is 2x, and across from 60 is x times the square root of 3. So now I know that x times the square root of 3 is equal to 4. It's my goal right now to solve for x so I can plug it in to figure out those other missing side lengths. So my first step in getting x all by itself is to divide both sides by the square root of 3. These reduce, so I'm left with x equals 4 divided by the square root of 3. Again, it's considered bad math etiquette to keep a square root sign on the bottom, so I'm going to multiply both sides by 1, or multiply both sides by the square root of 3 over the square root of 3. I'll squish up top, so I have 4 times the square root of 3, and on the bottom I have the square root of 3 times the square root of 3, which is the square root of 9, or 3. So I now know that x is 4 times the square root of 3 over 3. So I'm going to plug that in both locations here. So this chunk here, x, is just 4 times the square root of 3 divided by 3. And to figure out my hypotenuse, I have 2 times 4 times the square root of 3 over 3. So I'll multiply my coefficients, and I'm left with 8 times the square root of 3 over 3.